Hi, this is Sharon Rosenberg with another video of PSS showing you the power of the upcoming standard of PSS. DAC is behind us. This was a very exciting DAC for the PSS vendors, users, and Accellera. Accellera announced the availability of PSS early adopter version. You can download it. I placed the link right here and provide feedback. We highly recommend doing that. And please read through it, see that it matches your need. As part of that, we did a PSS tutorial and Accellera breakfast. Excellent questions from everybody and excellent answers. We did, for those who didn't see that, we did an intro for PSS and a demo showing the power. I provided a link here, and we're going to provide in this video two topics. One of them is how does PSS handle state variables and operation modes. We all know that, we all need that, low power, that's one of the big requirements out there. So how does PSS assist and support that? And the other topic is going to be the term graph and its relationship to PSS. There's a confusion in the industry, and we're going to clarify that as well. So let's talk about state machines and operation modes and how do we support that. I'm going to use one of the usage examples. As part of Accellera, we kind of ask users and vendors to provide some typical use cases that PSS will have to support, and low power, of course, was one of them. This set of usage examples basically describe the scope of PSS, which is very ambitious, as you guys know. So let's drill into this usage example, which was provided by a user. So the user defined the challenge to be that. So I have a product under test which has three power domains, A, B, and C. Each one of them can be in one of four modes. 0 is off, and 1, 2, 3 are functional states. You can traverse the state. You can only go one step up or down, consecutive steps, but as you do so, you do need to follow some rules. So forever, level A must be bigger or equal to level B. Domain C can be in functional mode if domain B is off. So this is part of the requirements, and what we want to do is we want to be able to make legal transitions, maybe exhaustive transitions. We may want to activate traffic, but of course you don't want to activate traffic if the power state is off, etc. And we want to do coverage for that. So this was one of the official use cases that will be provided with the standard as well. And let's see how do we first model the rules and requirements into PSS. So here it is. PSS has a built-in semantic for state variable, which you can read and update it. It's basically a struct, and let's go through it and see exactly how it matches for what the user wanted. This is the English section from his description. Each of the domains A, B, and C can be in one of four power levels. 0 is off, and 1, 2, 3 are functional state. You can just describe this in an integer that can go from 0 to 3, and here we have three different domains A, B, and C. The level for switch A must be greater or equal to that of B. No problem, that's a simple constraint. Constraint domain A bigger or equal to domain B. Domain C can be in functional state only if B is off. Yet another constraint on our domains. Constraint domain C different than 0, so in functional mode, implying that domain B is off. 0. Now there's one thing that was not provided but was clarified. They all start in their off mode. So here it is. This is how you write in PSS. Power state, initially, all the domains A, B, and C are off. And we're done with that. We've just modeled our state variable. Now, how do we implement a transition between the values and the levels? So Basically, making a power transition is a piece of behavior. It's an activity you can call. You probably will have an API to do that, whether it's a C API or a System Verilog API. So it's a piece of behavior, and the way to model pieces of behaviors in PSS is via actions. We're going to demonstrate here object-oriented, which is part of the upcoming standard. We also have aspect-oriented, but let's see how this look like. So here it is. It's an abstract action, which means you cannot instantiate that power transition. This is a superclass. So abstract action power transition. And here we are. Part of the attribute is the step. As you remember, we can go only consecutive. So you can go either minus or plus. These are the steps. We read in here the power state variable. Look at that. We're reading it in. That's an input. That's the previous value of a power state. And we're updating with the next level. So output power state. And we use a little trick here to say what we want to do. So by default, we have constraint A. These are named constraint. The next value is exactly like the previous. For B, it's the same. The domain B level is exactly the same as the previous, and domain C is exactly the same as the previous. However, and here's where we derive the concrete transitions. So a transition derives from power transition, so it inherits all that logic, but we're saying here domain A level is previous domain A level plus step, which is going to be either minus or 1. Constraint B is going to be exactly the same, so we're just overriding the section of B. A and C, the level of these domains will remain the same, but for B we're saying, well, domain B next equal the previous plus step, which is either minus 1 or plus 1. Here transition on C exactly the same, keeping the rest of the domains the same, and we're just changing the level of domain C. Now we're going to put here another power state observer. Just reading the current state. You'll see how this is very, very efficient for creating scenario, very, very powerful for creating scenario. This is something we've learned from experience working with users and from their needs, and you'll see how this provides some kind of a magic for what we want to achieve. So here is our transitions. A transition, B transition, and C transition, and we factored things out into an abstract power transition. So here's the scenario. The scenario I want to achieve here, this was part of the usage example itself. This is something the user said, oh, this is something I really want. This is how our use case, my use cases look like. So they wanted to try a full C between functional states of domain B. So here's how you do it. You define two parameters, which could is first B state, and we want it to be functional, so it's only 1 to 3. And here's the second B state we're going to choose, so it could go from 1 to 3. And here's our activity, and this is where we use the observer. Look at this. We're saying, well, we want first domain B to go to whatever is going to be randomized here, right? Here's the first functional state of B. Then we're going to take domain C to level 3, and then we're going to take domain B to the second B state. So what is it that we're achieving? We're basically providing milestones, and we're letting a tool that supports the PSS semantic to fill in the gaps randomly. Maybe in a way that we had to invest a lot of time on how to create those transitions and to make them legal, because there's rules on the transition. We cannot just take the state variables to wherever we want. The transitions have rules, if you remember from the previous two slides. So here it is. This is a solution. And for those who use for sequences, in sequences you need to provide everything. The tool is not going to provide the gaps, and definitely not take rules into account. This is the kind of solvability that you can get I hope you can see how powerful this is, but if you're not, we're going to look at the demo right now and I'll show you much more. So let's move to the demo right now. So here we are again with the composer, which is the main GUI of Perspec. Now, don't get it wrong. The fact that I can do things easily, it doesn't mean that this tool is just GUI. We have a powerful constraint solver, coverage engine, debug engine, etc. So the entire PSS semantic is right here. So what I did is I loaded the code that we've just went through. So I can click and you'll see in the source browser in here the definitions, and you can see our observer with the input in here, etc. And I even took the scenario, which is part of the official scenario, and you can see that the activity is right here. Go to a random B, go to C equal 3, and go to another random B. Okay, so let's start creating something simple. I'm going to drag this scenario in here. Basically, ask this scenario to take place. And I can click the solve button, and now the tool will show me one random way to one random completion to what we've asked for. So we're going to 1, B, then C, then we go to B again. So this is our scenario. If I'll click the solve button again, I will get another completion in here. Note that I can do selections in the GUI itself, so I can ask for a specific B to take place. I want the first B, the first target, to be 1, and the second target to be 3. I can do that, and I click the solve button, and I'll get exactly what I asked for. So let's just quickly look at it. We said 1 and 2, so if I look at the first B, increase the size for you guys. First B is 1, then the C equal 3, and then the second B is 3. Okay, so that's what we look for, 1 and 3. Okay, and if I click the solve again, I'll get a different random of transition that is taking place here. Okay, but now I can do something even more powerful than that. I can say, oh, please me all the possible random B's going to all the possible random B's around the C equal 3. And if I click now the fill button, as opposed to the solve, I will get a full space covered in here. You can see actually the mix. The tool is showing the mix of B's that took place, and you can see that the entire space is legal. So all of them are legal. I'm going to see an example which are illegal. Let's show you something interesting. I can, of course, suggest a transition. I can ask for a transition to take place. I'm going to show you that if I click the solve button, we get something interesting. We get transition of A taking place before the transition B taking place. Why do we get that? Let me show you various ways that the tool can help you with these kind of questions. I'm going to drag an observer in here, which means I want to put as a goal a certain state, a certain power state. And I can select that specific power state to be whatever I want. And if I click the solve button, it would just randomize one power state that was randomized. With the fill approach, I can say, well, I want all the combinations of B, as opposed to specific one, all the combination of B and C. I'll click the fill button. This is what I'll get. And look what you see here. We get a lot of combinations. Some of the combinations are illegal. Let's track and see why they're illegal. The ones that we did get, you'll see that if I'm going through it, you'll see that there's different topologies of scenarios that's just generated to meet our request. I can hide the illegal solution or not. That is up to me. So this is hidden and this is not. But let's see, why is this scenario illegal in here? What I can do is I can restore that scenario, basically take the same parameters, put them right here on the top. So I just took this scenario, these concrete values, and put it as my goal. And now I click the solve button, and this is why. Domain C can be in functional mode only if B equals 0. This is why this is illegal. Welcome to the era of PSS. If I had created a test like that, which was illegal, and I would run it, I would have to see why things do not work for me. I'll have to compile it, run it, debug it, and then I realize that there is issue with my scenario in here. This is not the case in here. We didn't run anything. Statically, the tool can tell you that this is illegal scenario, and you can do it to 100 and 1,000 actions. You can do it to 1,000,000 actions in post-silicon. The tool will statically make sure that your test is legal before running it, and it will explain why it is illegal. Okay, so this is the kind of automation we're talking about. Let me show you another thing. I'm gonna go back. Let's start a new thing, and I'm gonna create a power observer. I'm gonna create 2.1. Let's say I want to do something like this. I want to go to domain A being in all states, and then I want to cover all the possible combinations of B and C. I can mark these two and say I want the orange to be before the yellow. So all possible levels of A going to all possible levels of B and C. And I'll click the fill button right now. Think how powerful this is. I can walk all the path and just see what is legal and what is illegal with that request. By the way, I can do it. This is created individual scenarios, but you can do it in a single test as well. It's a matter of how many cycles you have, what is the platforms, etc. But it's up to you. This kind of definition. I hope this kind of shows what is the value, the solvability power of PSS. So one thing before we finish the demo, I loaded again the same model of the transitions and the power state observer that we have here, and here's our scenario. But if I click the button, you will find out we're loading in the C++ input format. Again, exactly the same semantic, but now it is all with C++ and classes and constraints and inputs and outputs and resources. So, and the state itself, right? The state variable. And, I can just go like this, and I will say I want to do fill of this and fill of domain C, and click the fill button, and we're randomizing our solution, and you can see the successes and you can see the failures exactly as the domain specific language, the DSL. And with that, I'm going to wrap up the demo and move back to the slides again, and let's continue with our second topic. Our second topic is going to be the term graph and graph based. There is a lot of confusion in the industry right now around the term graph based and what it means and what its relation to PSS. Graph is very fundamental notion, very basic one, useful mathematical notation in computer science, and generally there's different type of graphs, and graphs could be probably describe pretty much everything that we see around us. But we would like to go a little bit deeper, and would like to explain the differences between PSS and one sense of the term graph based, which is a decision graph, and a decision graph worker, a solution that works a decision graph. So I put here a behavioral model. You've seen that before if you look at the Accellera tutorial or looked at our previous video. So this is basically the start and the end point, and we have you are doing read in, passing a stream to the DMA, which is going to copy that to a memory buffer, these will work in parallel to each other, and then we're going to read from the DMA, mem to Q, pass it to the UART to do write out again, and then we're going to do a join and finish. So this is the scenario we've described, and we put it, this is the visual notations, but we put it inside our activity. Right? Here's the decision graph. So decision graph exists forever. Of course, they were adopted in 2007, 2008 by Brecker to do verification, and this is how the approach works. Basically, you span a space of scenario properties. It could be data, it could be timing, everything could be a decision. So you have either sequencing or alternation. Let's go quickly through this. So here's the top, and we can select one of the legal configs in here. And our scenario could be random or congest. And when we generate a packet, we need to first generate the address, then the length, and then the source. And these are all selections that we can do in our test. And here it is. This is a logical model to describe a test. Now they added also a new kind of constraint called the path constraint that are used to direct graph walk. So I can say either as a rule or in specific test, hey, if the config is 0, then always go to address 0. That would be a path constraint on walking a decision graph. Now let's take a moment and observe the differences between these two. Here's our behavioral model. We have a start and an end, and there is timing. There is timing here. This is the fork, and this is the join. And these two things will happen, these two activities, behaviors, will happen before these two activities. If you look at the decision graph, there's no notion on time, right? I mean, the gen packet could happen before we do the config and vice versa. These are just decisions. Now, this is a very generic model. I can do whatever I want, but it doesn't have built-in semantic for timing. So there is this shape of fork doesn't have any representation here. Not visual, not inside the input source. No fork and timing, no loops, right? I want to do a loop. Flow object. Where are the flow object? The input and the output, right, that we're using. They're not here, right? Of course, this is just a decision graph. It could be an object with constraint on it, not represented anywhere. State variables, what we've shown in the previous demo with the low power. You try to model that in decision graph, good luck with that. I saw many people trying. Resources. How do you model resources? There is a semantic to model resources. Control flow. Loops. I can model and I can visualize loop here. Data flow. The fact that we pass in the flow object. The bind directive. This is a behavioral model. Flowchart. This is what Accellera chose to be the standard input format. All these notations, all these semantics exist in the code you're going to write, both DSL and C++. So a PSS tool can take those and can analyze those. This is a state variable. I need to treat it like that. Oh, this is a resource. I shouldn't fork two things at the same time that use the same resource. Let me split the resources. We can do that analysis because you have that semantic inside the input format. It's critical for portability. Oh, I have a loop in here, right? Now I want to generate that loop to be in System Verilog or in C. The tool needs to understand that there is a loop. That's why you can do a loop inside the activity. We talk about quality. I mean, if I walk this decision graph, I would never get the contradiction, obviously, right? I'm just walking the graph. But if I describe a scenario specification, something I want to get, it will always be measured and compared to the rules, to the declarative rules. If it's possible, I'll get a solution, maybe a solution that is hard to achieve or I didn't think of. If it's impossible, it's a contradiction, and let me explain why. Exactly like we saw a demo. Okay, so well, a few FAQs about that. Will graph-based concept be added to the PSS in the future? Of course, PSS is evolving, new constraints are being considered, but if you look at the two approaches, they're totally different approaches, and in a way you can look at PSS and say it's a superset of what decision logical models can do. So, inside the activity, you can put select and you can put sequencing, but again, if you want to get more automation, more value, more portability, and of course more standard, you'll probably want to use the PSS approach, which is a superset of what you can express in decision graph. How to transition from a graph-based solution to the PSS? This is a tough one. We on a case-by-case basis, we can maybe carve some of the declarative parts into the standard PSS semantic. And if you're at the right time, if that's something you need to do, give us a call and we can walk you through and do the analysis and see if anything could be saved. And that's pretty much our summary. So just to recap, we look at the state variables and model operation, and in specific, we looked at it as from a low power challenge point of view. We can see how quickly and exhaustively we can visit all the state. We can define our own scenario and follow the scenario, taking the rules of our state variables into account. We discussed the term graph, what it means. We contrast the portable stimuli standard versus the decision graph, and the behavioral model, which is part of the portable stimuli, and that's pretty much it. So if you have any questions or any topics that you guys want us to discuss in the next video, please contact pssinfo@cadence.com. Thank you so much for the time, and I'll see you at the next video.